Okay, hello everyone. My name is Berk Brand. So this is joint work with several co-authors, and it's on power control for dynamic optical networks. So this was once portrayed as the picture of the internet, where you have millions of hosts arranged in this beautiful, colorful graph. But this is not the internet that I'm going to talk about. The one that I'm going to talk about is much uglier and hidden beneath the ground like this, which really forms the core of the transmissions. It's very ugly, it's very fragile, it's manually configured, costs billions of dollars to maintain, requires manual labor like here, and usually is found in holes like this one. But if you're a higher layer researcher like me, then your idea of optical transmissions is probably something like this. You have an optical link, you have bits that goes in on one end, and then they come out on the other end without being affected and at a very high speed. So the properties here are that optical links are high capacity, they're very low on energy, and they're completely error-free. So given these, it's curious why optical people have these huge conferences with thousands of attendees, because it seems like everything is solved and it's working. Well, I'm here to tell you that it's really not really the case. So first, in terms of capacity, so this is a graph showing the optical capacity that grows over the years versus the traffic of the US. So you can see that in the 90s, there was a period in which there was much more optical capacity that could be transmitted over a single optical link, but that the trend is far from continuing. And actually, the limit of optical transmissions is very much being approached with the current technologies. It is true that it's mostly low energy, but the error-free case is also curiously not really so. So this is a plot that shows the power on a link versus the error rate on that link. And initially, of course, as you increase the power, you decrease the error rate. But the curious thing in optics is that as you increase the power further, you get these other kinds of impairments that are shown here as acronyms. And these are very hard impairments to predict. They're almost impossible to analyze or to simulate. And essentially, optics is not an error-free medium. It's actually very much full of errors, but it's over-provisioned to the point where there is no errors. So essentially, the takeaway from this slide is that optical resources are also scarce, just like wireless spectrum, and that they should be used more efficiently, and preferably with input from the higher layers as well. So one way to do this is to do it through dynamic optical networks. And optical devices are becoming very dynamic. So if you go to one of these conferences, you will see that there are ROADMs that are essentially switches that allows one to switch wavelengths from one port to wavelengths to a different port, and do this at a very quick time scales by having little mirrors that move inside and so forth. There are modulators that can change the optical modulation on the fly, lasers that can change the wavelength of the transmissions, and filters and so forth. So devices are definitely becoming dynamic. And yet modern networks are very, very static. They don't change at all. If you talk to anyone from AT&T or Verizon, if they have a network that works, they don't want to touch it again. It's extremely fragile. It's extremely over-provisioned. They have very low utilization levels. Frequently, light paths are established but not used in case they will be used in the future. They have to be configured manually. A lot of times, you have to send out trucks to the field to make changes in the network. And they're extremely fragile as well. So let's say, as an example, that we have this topology, and we're a network operator, and we want to add a new path from Boston to New York. The way this is done now would be somewhat like this. You first send a truck out on the field at the first hop. These people go out with their machines, they make measurements, they verify all the optical links, make sure that everything is fine, and then progressively add just the first span. Then the second span is added, another truck is sent out, and so on and so forth until the whole path is added, which can take days, if not weeks, to establish, and is extremely costly. Now, one way to achieve this idea of dynamic optical networks, to self-configure optical networks, is through optical performance monitors. So these essentially are devices that continuously can measure the optical transmissions, report feedback to some control plane, and then allow this fast adding and dropping of light paths. And so this is what we're going to propose later, this control algorithm that uses these OPMs to control the power. And it doesn't do this just in isolation, but it does with input from the higher layers. So these can be input from the service level agreements that the network operator has with its customers, the routing and wavelength algorithms that decide on where the items will be, and protocols like GNPLS that also will decide on how things should be routed at the low layer. So in our idea tree, the operator now wants to add a light path very quickly between the same 2 points. This will happen automatically and progressively by these OPM devices continuously measuring the optical transmissions and providing feedback to the control algorithm and do this iteratively. So our contributions here are as follows. So we first formulate this power control problem that enables this kind of dynamic operation. Then we develop an algorithm that's based on these measurements to solve this control problem. And finally, we evaluated this on both a simulator and an optical testbed. So first, a quick intro into the optical transmissions and our optical model. So this is a very simple first hop of an optical transmission. You have a laser that creates a signal at a certain wavelength. Then this is modulated with data, goes through several kilometers of fiber, usually 70 to 100 kilometers. And then it's amplified by an optical amplifier, and then attenuated. And the reason why there's an attenuator and amplifier behind each other is that the properties of these devices can be different. So it's easier to attenuate selectively than amplify. So in this scheme, we propose the following notation. So first, our key variable is the variable P, which corresponds to the power of the optical transmission. So PIU is the power of wavelength I on a span U. So as this power goes through the fiber, it gets attenuated by amount alpha, and then it gets amplified by G, and then attenuated again by D, to result in a new power in the next span of the transmission. So these are all values in dBs. And here we can control alternatively either G by increasing the attenuation or by changing the amount of attenuation or amplification. Now in addition to this, we also add these devices, OPMs, to the network. So these are again these optical performance monitors that can provide information about the transmission. So here we use 2 types of devices, and they're clearly interrelated. So first are devices that provide the optical signal-to-noise ratio, and others report the bit error rate. And these are both functions of the power levels on those links. So this corresponds to the first hop of a several hop light path. And you can see this transmissions can happen at different wavelengths, different colors. And the rest of it is modeled in a similar way with these kinds of variables throughout. But the key point here is that these OSNR and VR functions, so we call these performance functions, and the core insight of this work is that the relationship between these functions and the P variables are convex relationships. So if you look at this plot again, so this is the launch power versus the bit error rate. The exact shape of this plot can be very different. The exact shape can depend on the temperature, depend on the right devices, the quality of the fiber, and so forth. But the key insight is that whatever the scenario, the shape of these graphs are always convex. And this is regardless of the modulation rate, here shown as M123. And we also verified this in a test bed by taking measurements, and this corresponds to the leftmost part of increasing power up here. So the key idea is that these OSNR and VR functions are convex and concave in P values. Now we formulate the problem as follows. So first we have the control algorithm that sits sort of in the middle of everything. And we have these constraints. So the VR functions are values returned by the OPMs. On the right-hand side, these are the threshold values that are given by the service level agreements. So these are thresholds that says a certain transmission has to have its error rate that is lower than a certain threshold. And OSNR has to be higher than a certain threshold. Then each of these constraints corresponds to a single transmission on the link. So if you want to add a new light path, let's say your routing algorithm wants to add a new light path, what happens is you add one constraint for each of these spans. So another line for the new light path to be established, and the algorithm solves it again. And if you want to drop a light path, you just remove those constraints from the set of inequalities. And this adding and removing, again, happens with input from the higher layers, other RW algorithms, or GMPLS-like algorithms. The key variable is the power variable P, and this is what controls the actual physical amplifiers. So if in this control problem you change the value of P, essentially the algorithm sends a signal to the physical devices to attenuate the signal or amplify the signal and so forth. So this is how we control what we control. And again, we have these readings from these OPMs from the lower layers as to what the transmission looks like in the network. So now we can formulate, this is the whole problem that we formulated. Again, so we have an optimization objective function, which is not actually that important in this case. So here we just are minimizing the sum of the powers, but this could be many other kinds of objective functions. But the most important part is that we're minimizing these powers while keeping these transmission constraints under their thresholds. So we propose an algorithm to solve this. So the algorithm is called simple. So given that these functions are convex, the previous problem formulation is a convex problem. And this algorithm that we're proposing is also a convex solver. However, this problem has very unique constraints. So first of all, it runs on a live network. So this is a very uncommon in real convex algorithms. Normally, you solve the problem, you get the output, and then you use it in some way. But in this case, this algorithm is actually running on a live network. So what this means is that the algorithm cannot just change the p-values as they want, because this will correspond to physical amplifications being changed. Secondly, the SLA requirements, these constraints, are actually more important than optimality. So typically, if you have a convex algorithm, you want to find the optimal solution, whereas in this case, it's more important to find a feasible solution as quickly as possible, as opposed to being an optimal solution, because the operators really don't care if the minimum energy efficient version or not. Thirdly, the functions, these curves, are actually not known in advance. As I said, these curves can depend on many things, and it's very hard to have a model that really predicts this. So we don't assume that these curves are known in advance. We still assume the convexity, but we don't know the curves. And as a result, we also don't know the derivatives of these curves, which is again what most complex algorithms use. And secondly, this algorithm is run continuously on a live network. So it's not like something that you solve once and then you use it, but you just run it over and over again in succession. So this algorithm is basically an algorithm based on a direct search method. So I'm going to quickly run through the way it operates. So let's say the current power levels in the system is denoted by P1, and then we return the values of the OPMs. The OPMs make a measurement, and this is the first blue dot. So what the algorithm does first is that it picks a direction from a set dk, and then it just tries to take a step in that direction blindly. And then it evaluates, it makes the change in the network, and then takes a measurement again from the network. And this is the next point, P2. Now, since this was a good step, now the algorithm increases the step size by a certain amount of theta plus, which will become important later. And let's say it takes this step size to obtain this red dot. This is clearly a worse point than the previous one, so this was a failed step. So what it does is that it decreases the step size by an amount of theta minus. And then it tries to do the step again for the second point. And then it just repeats this until the step size gets very, very small. And then at the end of the day, by repeating it, it comes to the point where an optimal solution is found as P star. So note that for this, we didn't need to know what the curves exactly look like. And what's really important here is also that in reality, since we're making measurements, there's a lot of measurement noise present. So this should also work even when the curves have unknown Gaussian noise. Now the two most important parts of this algorithm is these parameters, theta minus and theta plus. So theta minus is a parameter that chooses how to decrease the step size if you made a bad step. And theta plus is how much you increase the step size by if you made a good step. And you'll see that these will become very important later on. Another important parameter is the set dk from which you choose the directions to try. And to come up with this set, we have different heuristics. And I'm not going to go into too much detail of these heuristics, but essentially you can either just try the coordinates directions, or you can do something smart based on the history of how you'll come to that point. But I'm not going to go into too much detail, so I'll refer to the paper. Now, before I go into the evaluations, I want to just introduce one simple impairment that we use so to give you the idea of what we do. So let's say we have these two light paths, lambda 1 and lambda 2, going into the amplifier, and they come out on the other end being amplified. So let's say we now increase one of the input values, lambda 2, above lambda 1. What this does on the output is actually increases lambda 2, but it does so by decreasing lambda 1. So this is known as gain stealing, and it happens because these amplifiers have a constant output power. So when the amplifier is saturated, increasing one wavelength can actually increase the power on the wavelength, making it lower than it should be. So this is an impairment that we'll use in the evaluations. So now we simulated the setup. And we did this on an optical simulator with 6 nodes. So this is the Géant topology. And an optical simulator is especially a very low-level simulator that really takes into account these impairments. So I'll show you some sample results, and then I'll get into the main results. So here we have an optical trace. So first notice that on the x-axis, it's over the number of evaluations. So these are the number of OPM evaluations that it takes the algorithm to do. So the computation of the algorithm doesn't take very long because it's a very simple algorithm. But the main bottleneck here is the amount of time it takes for a single OPM to take a measurement. And in current technology, the ones that we use in our testbed, it takes a minute or more to get a single point. But there are new proposals of OPMs that will reduce this dramatically to even milliseconds to make a single measurement, in which case the time scale will shorten much, much more. So in this case, again, the x-axis is the number of evaluations, so you can think of it as time. And the y-axis is the power levels, here shown as the attenuation. So initially, the green light path is present, so it has a certain attenuation level. And then the other 2 light paths have very high attenuation levels, so they're not existent. And what we do is we give the algorithm that we want to have all these 3 light paths present, and we just run the algorithm on this control problem. And what happens is that progressively, again, the 2 light paths gets added, measurements are made, and the green light path is also tweaked accordingly, because otherwise it would not satisfy the threshold any longer. Now, what we did was to run the exact same experiment now, but with different sets of parameters, theta minus and theta plus, just to show you the effect that these parameters have on the convergence. So if we pick a different set of parameters, which I'll get to later, you can see that the convergence is now much, much less smooth. There's very many fluctuations, and it just keeps bouncing on and off. However, you can also note that the convergence is now much faster. Instead of 600 evaluations, now we do the same in 120 evaluations. So we ran this experiment over and over again to understand the effect of these parameters. And so these show when we fixed one of the parameters, theta plus, to 1.2, and we increased theta minus by a certain amount. So I will show you the curve, but I don't want to use the laser pointer, but since we're doing things like Gauss, I want to also do it like Gauss. So here, theta plus is set to 1.2, and theta minus is increased from 0.6 to 0.9. So here, this metric is the standard deviation, the fluctuation in the convergence. So a large number here indicates that the function fluctuates very much. And here, this is the convergence time that sets how fast it takes for the algorithm to converge. So as you see here, if we pick this 0.6 value, we get a very high fluctuations. The standard deviation is very high. However, in exchange for the same value, the convergence is much, much faster. And we can see that the trend is that if you increase this value, the fluctuations decrease, but the convergence takes also longer. And this makes sense because theta minus is by how much you decrease the step size. So if it's 0.6, you're essentially decreasing it by 40% every time, and 0.9, you're decreasing it by 10% every time. So you can see that there's a fundamental trade-off between fluctuation and convergence speed. And we also note the same for when we fixed theta minus to 0.6 and now modified theta plus. We can see that again, higher fluctuations mean faster convergence and vice versa. So this is just to show that it's very important to find the right theta parameters so that you get fastest possible convergence with decent convergence characteristics. Now also in real networks, the noise is always present. So what we did was to add noise of different amounts and see how that affects the convergence. So here we have the noise variance on the x-axis versus, again, the standard deviation. And now we have here the probability of convergence of the network. So we can see that if there's little noise, again, the fluctuations, there's very little of them. But as we increase the noise, the fluctuation levels goes very high. And if noise is very, very high, there's really no fluctuations. But this is because the algorithm really doesn't converge at that point. So clearly, the less noise, the more noise there is, the probability of convergence also goes down. Now, this was all simulation work, but we also have experimented with the setup. So this is a rather simple experiment, but it's very telling because it uses off-the-shelf equipment, but real telecom equipment. So here we have a single hub, essentially, over 25 kilometers of fiber. So this is the 25 kilometers. It's full of fiber. Over here you have 8 lasers that again generate light at 8 different wavelengths. And these are all multiplexed onto a single fiber. So then this goes to 25 kilometers, and then it's measured at this point by this BERT, which is a function, kind of an OPM that measures the bit error rate. And this is all controlled by an central controller, which you can think of as somewhat like an STN controller of sorts, that controls the power levels through these attenuators and makes measurements using the BERT here. So this is the setup. Again, just a picture. You have 8 light lasers lined up over here. And then this is the bit error rate measurement tool here that gives away the bit error rate. And this is a very old tool. It takes several minutes sometimes to take measurements. So what we did here is we ran an experiment that will simulate sort of the operation that a dynamic optical network should have. And the details are not that important, but essentially we add wavelengths, drop in a wavelength, and add and drop, and so on. But what you can notice here is that, again, the convergence is somewhat smooth, and it takes about 700 evaluations to do. Again, this is the exact same one, now with a different set of data parameters. And you can see that now the convergence is very erratic, but the same scenario takes only 160 iterations as opposed to 700. So finally, our contributions are as follows. So we formulated the control problem. We developed the algorithm to solve it. And then we evaluated this on simulations and on a testbed. And we feel like this is sort of a first step towards optical STN for optical networks that should work with input from the higher layers. I think there's a big disconnect between the optics in the lower layer and the higher layer algorithms, and work like this could help converge the two in using this STN architecture. So that's me. Thank you.